So where we end up last time? We end up here. So now we will study the effect of proportional control of a second order system. We have this second order system, which is in this case 1 over s square, 1 over js square, and we have proportional control. So what's the effect of proportional in this case? If I ask you what is the open loop zeros and pole for this system, what are the open loop pole and zero for this plant? Yes, students?
S equals 0.
S equals 0. So I have two poles at the origin.
Yes.
If you wish. Two poles at origin. Two poles at origin. So the system is stable or unstable? The open loop system. That's my plant. My plant is stable or unstable in that case. This is a stable system or unstable system? Yes? Is it a stable system or unstable system? If I have two poles at origin, the system is stable or unstable? Students?
Yes, doctor.
Yes. So
when it's on the origin, it's marginally stable.
Okay. Looks like we have Pamal des étudiants. Many students are here, so please participate. Two poles at origin. Okay.
دكتور انا هلا بعدني فاتح التيمز كان معلق عندي.
أهلا وسهلا. So two poles at origin. Remember, if you go back to this slide, I was telling you to stability slide. If you have poles at the imaginary axis on the same place, wherever here or two poles are, the system is unstable. So if you have two poles at the imaginary axis on the same place, like same poles, two same poles, not two distinct poles at the imaginary axis, this is unstable system. However, if you have two distinct poles at the imaginary axis of your second order system, so this is a marginally stable system, as you said. Yes, this is marginally stable. But if in this case the system is unstable.
طب دكتور كيف ممكن يكونوا two poles at the same location?
Like this case, for example. 1 over j
other than the origin.
I don't think for second order system you don't find. That's the only case.
Yeah, but that's why I said marginally stable.
So the system is unstable, right? System is unstable on open loop. So what if I add Kp on it? How this will shift the open loop poles? How this will shift the closed loop transfer function or the closed loop system as a whole? How the poles will be moving? So to answer the question, you need to find the closed loop transfer function C over R. So C over R, forward over 1 plus loop, you get it. So then if I ask you, after finding the closed loop transfer function, the second question will be, where are the open loop, where are the closed loop poles of this system? So if you have the transfer function now, you need to find the closed loop poles of the system. How do we find them? If this your
we divide by j first.
Yes.
To write the characteristic equation.
So usually
the denominator will be s squared plus
y axis.
Yeah, usually as a thing, characteristic equation is always the denominator. Denominator is your characteristic equation. So then characteristic equation equals 0, you can get the two poles.
بيطلع على الواي اكسس.
They shifted apart on the imaginary axis.
Very nice. So now my plant was unstable with 2 pole here. Then after adding proportional controller, the gain K move up but still in the imaginary axis. So now what's the effect of increasing Kp? What will happen to my pole if I increase Kp? So imagine this my imaginary axis.
They will go further apart.
Apart, huh? Very nice.
Yes.
So then so now maybe I will get 2 here. If I keep increasing, I will get 2 here, and so on and so forth. And this is, we know this is omega d. So basically what you are doing for any value, so what's the conclusion here? What's the effect of Kp or Kp controller on a system like this? On a second order system like this? What's the effect of increasing or decreasing Kp on the system? Is that will make the system stable? Adding proportional will make the system stable, for example? Is there a value?
Marginally stable.
Yeah. So then is there a value for Kp that makes the system stable or not?
No.
There is no. There is no value of Kp that makes the system stable. The system will keep oscillating and oscillating. Like if I have a reference of 1, the system will going to oscillate around 1. Your C of t will be oscillating around 1, as you can see here, for a step input of 1, for example. Then increasing Kp, all what it will do is it will make the oscillation faster. Like instead of going this way, maybe you go faster, like like faster. Keep increasing Kp, so it will oscillate faster and faster. Like you decrease the frequency, you increase the frequency, decrease the time. That's the only effect of Kp, but they don't shift the poles to a stable location. Good. Any question regarding this slide, the effect of Kp on this system? So let's see if I add a proportional derivative controller, PD controller. So now to my system I'm adding PD controller. This is my plant, and I know my plant has 2 open loop poles at the origin. So now where will be the poles after adding proportional derivative controller? I need to find the closed loop transfer function. Forward over 1 plus loop, you get the closed loop transfer function. Where are the poles for the closed loop transfer function? So I need to find the characteristic equation roots. So the characteristic equation is the denominator equal to 0, which is this one. That's the denominator equal to 0. So I need to find Kd. If I have value for Kd and Kp, I can find the closed loop poles. So then it's you, the designer, to change Kp and Kd, or Kp and Td. You are the designer. You can put them in your desired location. Depends in your desired response. Depends on your specification. Which settling time you need. Which overshoot you need. Which maybe omega n you need. Right? So then if you know your overshoot, your settling time, so you know where to locate your poles. Depends on your desired response. So then depends in Kd and Kp, maybe you need a critical overdamped system. So you choose Kd and Kp that give you a 2 distinct real pole. So then you are shifting your 2 origin poles from the origin to these 2 different locations. So then your system will be, in that case, critically damped system. If you wish, in yellow. a critically damped system if your poles are here. If you decided to have poles maybe somewhere, two distinct poles here, two same poles at same location, so here critically damped system, not over damped, maybe critically damped system, so then maybe it's little, maybe the difference in between them is not too much. Or maybe you wish to have poles in here, so then you need to shift your pole location from here, this two pole from here to here, so you make your system go this way. So you are the designer, you can choose P and D that move the system from instability behavior to a stable behavior. So then derivative term, as you can see, introduce damping effect that stabilizes the system, which was originally oscillate indefinitely, right? Because you have with proportional you had only two pole at the imaginary axis. So you get the effect of adding the PD controller on this type of system? Is it clear?
Yes, doctor.
And by the way, just usually I like to ask them in the exam same, just to check understanding as concept question. So I usually ask this kind of question. So you need to do the derivative and ask this kind of hint. What's the effect of proportional derivative? Where are the open loop poles? How the closed loop pole will be changed? Depends on the value, taking this value of Kp and Kd, how this will affect the dynamic response. So now, what about disturbance rejection? And this is important. Disturbance rejection for without integrator. So let me copy paste it to whiteboard here. What's this? Why it's so small? So we need to go 100. Yeah. Okay. So now quickly let's study the effect of adding disturbance to a system. So what's the effect of adding disturbance? Assuming I have step disturbance here added to the system in the presence of proportional controller, and that's my system. So imagine now you have your DC motor and doing position control, because this is exactly the same, or you are doing joint control for a robotic arm, right? So somehow similar system. So then in joint control problem you need to control the joint angle, and you may most likely to have disturbance on the system. What if I have proportional controller also? How this will affect is that will eliminate the disturbance, or the proportional control doesn't cancel disturbance. What do you think? So this is a question, how the error will be affected by disturbance. How the error will be affected?
It doesn't reject.
It doesn't reject. Proportional control doesn't reject disturbance. See, the important term, we keep repeating them because so we need to fix the idea for everybody. So make sure you end the course and you understand the more important terms. So yes, we will go again about this kind of things. Okay, my error equal to minus C of S in case of R of S equals 0. So this is a linear system. I can take for now R equal to 0, and I keep having only one input to my system. So now my system has only one input, the disturbance there. So if I have the disturbance as input, okay, so then here is, they call it T, usually we call it U, but it's alright, and this is your Kp, and this is the error.
P -1, doctor.
Very nice. So this is -1, and this is C. Okay, so then here you have 1 over S GS plus B.
دكتور بالهوم ورك بتاعت البي اي دي في شغلة بتشبهها
or okay.
وفيك تفتح لنا الفايل كرمال السبمشن.
Because I didn't finish the chapter, but I think yes, you're able to start submit it now because you have the knowledge to make everything. But the reason just I said let me finish the chapter before, but yes, I will do, no problem. I'm not going to put deadline, but you can still submit if you feel you are done with. So now your system is like that. So if you want to find C over D is a closed loop transfer function, C over D of S. So I'm cancelling the reference, taking it as 0. This is what is forward over 1 plus loop or 1 minus loop.
1 minus loop.
So forward over 1 minus loop because
أو بنشيل الماينس 1 من تحت بنحطها 1 over
yeah, yes,
plus.
yes, you can put minus here, no problem. So then you can find C over D, the transfer function C over D. Just to don't lose time, it is easy derivation. It is this how, that's the transfer function C over D. It's not an image, so we cannot take GS square BS plus KP. One over GS square plus BS plus KP. If I'm not wrong, there is nothing in the denominator, right? Sorry. There is nothing in the denominator. Okay, so this is your transfer function. Again, the error equal to, in this case, minus CS. The error which is here is minus CS because the reference is 0. Then if I want to find E of S over D of S will be minus C of S over D of S. So then E of S equal to, that's why I divided by D, because at the end I'm looking for the steady state error in the presence of disturbance, how the disturbance will affect my error, how disturbance will affect the steady state error. That's what I'm looking for. So I need to find the steady state error, so that's why I need to find E of ES, Laplace of S. So then minus C over S, which is this one, 1 over GS square plus BS plus KP times D of S. D of S is 1 over S if it is unit step, if it's unit step.
دكتور في النيجاتيف ساين بس نسيتها.
Yeah, thank you. So then the steady state error according to final value theorem, limit 1 S tend to 0 of S E of S, so S by S they go, then you get up ending 1 minus KP. If the system is stable. If system is stable, I can find the steady state. So then, in the presence of disturbance, the disturbance doesn't eliminate, the proportional control doesn't eliminate the step input, doesn't eliminate the step. According to here, because the steady state error is not 0. Right?
بس دكتور فينا نعملها decreasing صح؟
You can decrease it by increasing KP. Yes.
Yes, but ما بتصير صفر.
Yeah.
ما بتعمل elimination.
If you wish, here if you want to compute the whole system, you have C of S. The whole output is C of S over R of S when D equals 0, right, times R of S, if you remember we did it before, plus C of S over D of S when r equals 0 times d of s. So that's your actually your C. According to the superposition theorem, you cancel this first and then later on we cancel this and you add them together, you get your output actually in the presence of disturbance. So then in the presence of disturbance, that's how the system will look like. In the presence of disturbance 1 over s, if I want to find C steady state, for example, I find this steady state, I multiply by 1 over s, or you can do the calculation yourself, and you find like what we like to have a steady state value here tend to 0 in the presence of disturbance. So then I can, and this is tend to 1, then I can have C tend to R. But here C doesn't tend to R exactly, even if, because I have here a term here, which is 1 over Kp. 1 over Kp. Good. So the conclusion here is a proportional term doesn't eliminate the disturbance. So system cannot reject unit step disturbance. Any question regarding the effect of proportional term on the disturbance? So when a unit step disturbance is injected to the system, a proportional controller cannot reject this disturbance. So then the question, what if I add an integrator? You do the same. By adding an integrator, you increase the order of the system, of course. So then that's your closed loop system. It looks like this. We do the same, error equal minus C, and you find C over D, transfer function. Then you can find the steady state error by applying the final value theorem. You get a steady state error equals 0. Then what's the conclusion in here? What's the effect of PI controller on disturbance?
So eliminate the steady state error.
It eliminate here the disturbance. You're talking more about disturbance. It means there is no error related to disturbance, right? Because here the only input you have is disturbance. Take it as simple. I assume I don't have a reference, but usually in real case we have reference. But here just let's separate the system. As in linear system we can separate input and output. So imagine the R doesn't exist, the reference signal doesn't exist at all. But in reality it exists, as I explained to you here. So you should have referencing. But so you add them all together. At the end your output is the summation of all the output from different input. So now assuming I don't have, I only ejecting disturbance. If my reference is 0 and I have no disturbance, in a real scenario my output should be 0. But now when I'm adding disturbance in case of proportional controller, so I have an error signal. So means the controller doesn't reject my disturbance. But in here the controller rejects the disturbance. When I'm adding disturbance, steady state error still 0. So at steady state rejected. So it will be affected at the beginning, but at steady state it will reject it. Good. Any question regarding the effect of what's the effect of? So what's the conclusion? What's the effect of adding an integral term?
Integral terms eliminate steady state error.
Yes, and regarding the disturbance, what's the effect on disturbance?
It will reject it.
It rejects the disturbance. So system can reject unit step disturbance because when I inject the disturbance, I look to my output. My output still a 0, still 0. in this case. My steady state error is 0. That means it completely rejected disturbance. Keep in mind here, I'm not finding E over R. So here, not E. I'm not studying E over R and telling you, talking about steady state error. Here that's right. Maybe it confuse you because you're computing the steady state error. That's right. At the end, we are computing the steady state error, and that's the steady state error. But we are studying the effect on disturbance. So that's why I'm dividing E over D, not E over R. In this case, because if you want E over R, the E actually is not minus C. The E is not minus C. E is equal to minus C only when R equals Z. Otherwise, E equal R minus C, as we are doing when we did the steady state error calculation. So here is it, when I ask you to eliminate the to study the effect on disturbance, so you need to do it this way. This is an important slide. How I can copy paste the slide to my Windows. I cannot. Maybe I need to use Paint. Okay. This is an important slide. So we'll be talking about okay. Let's make it bigger. So what do we have in these two cases? A case, let's see, figure A and figure B. If you look at them, figure A, this is figure A. Okay. No, not this. This is not the pen I want to use. I want to use this one. This is figure A, and this is figure B. Here, they are asking us in this slide to study PD controller, if you wish, PD controller versus P controller and velocity feedback. So this is PD controller. This is PD controller here. And here is P controller plus velocity feedback. Here is velocity feedback or derivative feedback, as in your project. In your project, I'm asking you to add 1 plus, so you have velocity feedback. So we need to compare these two controller. This alternative controller of PD. This is PD controller and this PD controller. But this we call it P controller plus velocity feedback, or plus derivative feedback, or plus rate feedback. Velocity, derivative, or rate feedback, because you have the S in the feedback. So you are feeding here. So here, like, what do you have here? Actually, you have, if you want, so in this system, actually you can replace this by, it's exactly the same of saying KD over KP S, and both they go and you add them here. Okay, this is minus, this is R. Okay, then this is KP, and this is 1 over GS plus BS, right? This is the same system as that, right?
دكتور بنوصلهم دغري ببعض ولا بنحطهم على الصم؟
You put them on some.
يعني بنحط كي دي اس اوفر كي بي بلس
Yeah,
اللاين اللي لحاله.
yeah, you are right. Thank you, Tarek. So, right, this is equivalent to this type of system, if you wish. So then, what you are doing here, you are feeding back the output, and you are deriving the output as well. So in the first system, here is not PD controller. Let me check the slide again. Yeah, it looks like I was taking something which I don't know. That's the slide that I want. Let's say that's what I want. So this figure A, if you wish. Okay. So yeah, in here, in case A, you have PD controller. So you are doing your controller, you are doing proportional of the error and you are deriving the error. You have proportional of the error and deriving the error. But here you have proportional of the error and you are feeding the error back, but you are deriving the output, doing a derivative to the output, not to the error. And this is also a PD controller at the end, a different alternative of PD controller. You can take it this way, 1 plus KD over KPS. And here you have KP. So different variety. This is a PD controller, this PD controller, but this is the exact name, we call it proportional plus velocity feedback, or plus derivative, or plus rate feedback. So when you hear this term, so you know you are your KP and KD design are here. Okay. So then why we want to use this alternative B? But I can use this. Why do I need to use this alternative? Is there any benefit of B compared to A, or no? They are the same. What do you think? Is there any benefit to use the other alternative of? Well, we cannot know until we look to the closed loop transfer function and to see how this will affect the closed loop transfer function. So then if I find C of S over R of S, it's easy, right? Forward over 1 plus loop. And for this one, C of S over R of S, let me put them in just close to each other, so at the same level. Alright, so then here also it's easy, C of S forward over 1 plus loop, right? So then I don't want to spend time, I copy paste them from my paint. So then this is
دكتور عمل كوبي للمور سمبليفايد في بعد وحدة تحتها كان to be able to compare يعني.
yeah, I didn't see one. Let me go back. This one.
Yes.
Yeah, thank you. Yes. Alright, so now this is what we want to copy, and the other one is this. Good. So then this is a transfer function. Is there any benefit of B compared to A? What do you think? why do I need to go with the alternative PD control? Why do you think this alternative is important? I need it.
No zero, no effect of zeros.
Very nice. So here there is no effect of zeros. If you look to the poles, poles are the same. This and this have the same pole, same denominator. So then my closed loop poles, if I want to find the closed loop pole for the system, they could be, and they are the same. But the only thing is, in here you have 0, in here you don't have 0. So then here you have effect of 0, and we know the effect of 0 is not desirable. It doesn't, if the 0 is in the right half plane, like self-balanced robot or a stick balancing a stick, inverted pendulum, so you need to go down than going up to reach your desired. And if it is in the right half plane, then you will increase the overshoot, make the system faster, but you will increase the overshoot. So in both scenario, having 0 is not desirable. So then in the classical way of PD controller, so you should know that when you're adding it, you are adding a 0 to the system. You see it? There is clearly 0. So how to try to avoid this 0 term? So put your do a design of proportional than proportional plus velocity feedback. And this is you don't find in your PID function that you get when you install the library, just the inherent library. You don't have this variety of options. So then yourself, if you want to make something maybe better, so you need to make the library yourself and have a feedback derivative control. In the library, what they are doing, they're adding filter to the derivative term to reduce the noise effect of the derivative controller. But they don't use rate feedback control. Okay? So then if you are programmable, you're able to do your own function which suit your needs. Okay, instead of be a user and just keep limited by the function provided by others. Okay. So then this variety you don't find. Later on, when you learn cascade controller, maybe you need to have two loop control together. This you can still add to PID library in a way you do cascade control. But maybe it's better if you make it yourself. Make a cascade controller yourself for PID. But to be honest, it's easy to add two libraries together and use them. Also, using from others, it's a very important thing because you save time. So you stand on their shoulders to get higher and higher, right? And this is very logical, and that's how generation to generation they get improved, because we take science from others, so then we go step forward. Okay, so we don't reinvent the wheel each and every time, so you don't need to recreate and reinvent. Good. So in here you need to avoid the 0 term. So then if you need to avoid the 0 term, don't use the classical PD controller, use P plus rate feedback controller. Good, or velocity feedback controller. Any question regarding this slide, which is here? Is it clear? Good.
Yes, doctor, clear.
Okay, so yeah, this I skipped them. Just the effect of 0 we already saw before. Summarizing PID controller, proportional control action. This is a summary of what we did in this course. Proportional control action, increase speed of the response. If you remember, it was increasing the speed. Basically, omega n increases. Omega n is related to the speed of the response. But this is becomes more clear when we do frequency response analysis. Not like now we are always doing time domain analysis. We have function of t, but we never studied in frequency domain. As in your project, in the project description, I was doing some frequency domain analysis and I drawing for you body diagram. Okay? But this they are proportional. Omega n increase when you increase the speed. When you increase the proportional term. So when Kp increase, the speed of the system, speed response will increase. That we noted, right? And stability will reduce. But for the integral or control action, improves the steady state performance. Okay, it improves the steady state performance depending on the system type. If the system of type 1, then maybe step input it eliminate the steady state error. But if a system, but it doesn't eliminate a steady state, it doesn't eliminate the error, steady state error for a ramp input. But for a step input it eliminates. So it improves the steady state error in any case. Slow down the system. We saw that it slowed down the system. It reduces the stability. It increases the system order, and it rejects disturbance. So some plus, some minus, right? Some minus, some plus, some minus, some plus. Okay. Derivative control action, add damping to the system, improve stability of the system. Right. Also make the system slower, if you wish. No, doesn't make the system slow. Derivative term. Let's see here the summary here in here. Okay, this is table, it resumes. This is we're taking from Wikipedia. KP. If I increase KP, how this will affect? Let's take this out for now. If I increase KP, how this will affect the overshoot? Overshoot will increase. What about the steady state error? Will decrease. What about stability? Will degrade if I increase the KP. What about KI? If I increase KI, the overshoot will increase as well, and the settling time will increase. That's why I make the system becomes slower, because the settling time will increase. It eliminates the steady state error. Well, it eliminates in case of a unit step input, and it degrades the stability, of course. But what if I increase KD? It will decrease the overshoot. We saw that. Decrease the settling time. That's why I want to say it actually slow down the system, speed up the system in terms of settling time. It will settle faster because when it decreases the overshoot, so you will have less oscillation, so you will reach your settling time faster. Makes more sense. Okay. As for the stability, in case of KD small, so there is no noise effect, it improves stability in case of KD small. Effect of noise we studied in part 1, right, before. So we are not going to recap on the effect of noise for the derivative term, but we did it before, or we did for proportional. So it amplifies, but also the derivative amplifies it. All right. As for the rise time, you can look at the rise time. Increasing KP will decrease the rise time in case of what do you mean by decrease the rise time? So it will reach it will reach the reference fast. So that's the rise time faster. Same for KI, but make this. That's why the overshoot. So you see the terms are related, of course. So that's why overshoot is increased, because you will fast reach your reference, but this may lead you to overshoot. Doesn't have really a lot of change on KD on the rise time. Okay, but KI and KD affect the settling time. KD decrease the settling time, so system becomes more faster, and in the sense you reach the steady state faster, less oscillation. but here it increased because overshoot will increase and so on. Any question regarding the summary or regarding PID controller as a whole? Yes, no, clear?
دكتور
Yes.
قطعت الكهرباء for 5 minutes
Hmm.
ما انتبهت شو قلت.
It's all right. But it didn't say like you'll repeat. You'll go over it later. Not really. You know, Tariq, you don't ask me to repeat for one student. Please, I give you favor for you. I know, but I cannot do that. No,
Okay.
otherwise it's gonna be discrimination. All right. Uh, determine the value of k and k such that the closed loop system has a damping ratio of 0.7. So let me take this image and put it here and do the exercise. Okay, so just I want to call them K1 and K2 because small k and big K doesn't really, you know, we may get lost easy when we are doing the calculation.
بتضيع.
Yeah. So then find the value of k and k such that the closed loop system. So pay attention to the question. Such as the closed loop system has a damping ratio equal to 0.7 and natural frequency equal to 4 radian per second. So the closed loop system has this characteristic. Those are the characteristics of a closed loop system. So then how to go in this exercise?
أول شيء بدنا نطلع الكلوزد لوب اللي هو معطينا يعني صح؟
Very nice. No, you need to find it yourself. Like here, maybe I did the solution. I'm solving it. So then, yes, you need to find C of S over R of S, right? And how difficult is finding C of S over R of S?
ترى أول شيء ما نعمل هاي اللوب الصغيرة اللي جوا.
Okay.
الصغيرة وبعد
So then K1 S plus 2 K2 or no? Am I right?
لا دكتور بدك تشيل كاتو من فوق.
Okay.
على 1
Over 1 plus this is forward over 1 plus loop. So then maybe better to divide the problem, right? No, don't because otherwise you may get lost. So then R of S, and in here you have 1 over okay guys, let me then here you should have 1 over S, then 1 over S C of S, and here you go, right? So now for this you can do also forward over 1 plus loop. Over 1 plus loop, which is K1 over S plus 2 over 1 plus K1 K2 S plus 2. Alright. So forward over 1 plus loop. So this is keep the same here as here. 1 over S. right? So this is forward over 1 plus loop again, and then you do the derivation and check it at home if it's correct or not, right? You get this transfer function, which I'll be taking it out from here. But let me just replace the big K by K1. So then it's K1, K1, K2, K1. That's the closed loop transfer function. So from here, how to go? You have omega n equal to 4 radian per second, the angular velocity, and you have the damping ratio equal to 0.7.
Yes, we put K1 squared equal K1 squared equal 4 squared يعني.
Yeah, okay, yeah. So that because you said you want to go and compare it with plus omega n square, to compare it with the basic form, and this is your closed loop poles. So if I ask you what are the open loop pole for this system, we don't really know where is the plant actually. I don't know where is the plant in the system. Basically, is it 1 over S, or so we cannot really look at it this way. But I can know at least my closed loop poles where they will be. My closed loop pole will be in a place where omega n equal 4. So probably if this is omega n 4 and with zeta equal 0.7. So if this is the zeta that's giving the 0.7, so then my poles will be here. So I can know my closed loop pole where they will be. By omega n and zeta equal to that, I can locate my poles. So I'm choosing K1 and K2 that make my closed loop poles at this location. So now that's your role now, to find the K1 and K2 as a designer. In a way, your response will have damping ratio of 0.7 and omega n equal to 4 radian per second. And from here onward, is it clear, or you need to continue? Is it clear how to continue from there? Do you need to do the derivation, or it's
ايوه تعمل
Yes,
كومبير
Dr.
بس.
clear, right? So omega n square equal K1, so you can find K1. Because so K1 equals square root of omega n square. So which equals then K1 equal to 4. Or K1 equals 16, sorry, right? Sorry, K1 equal omega n square. So K1 equals 16, and from here you have zeta and omega n, you can get K2. All right. So now in this 15 minutes, remaining 15 minutes, we'll talk about tuning, so which is very important topic in control theory. It's experimental determination of the parameter PI and D. How to experimentally determine the PI and D parameters. Majority of industrial controllers are PID or PID derived controllers. Like PID derived controller could be P controller or PD or PI, okay, or P plus velocity feedback. Okay, those are PID derived controllers. Also, we may see later on when we go to root locus, hopefully we'll see lead and lag controller. Okay, those are all PID derived controllers. Lead, if you want to look for, and lag controller. So these are also variety of PID. Lead, if I remember, is like PD, and lag like PI. And when you combine lead and lag, so you'll get like kind of PID, same effect as PID. So this PID there, or PID derived control. Also, it may not be the optimal controller. It's simple to implement. So that's why majority of industry controller are PID. Most are configured and adjusted on site. The parameters are adjusted on site and can be done with minimal background in controls engineering. You don't need to take control course to know how to tune the PID parameter on site. Just you keep tuning them and you look to the response until you get track on. That's what I'm saying. Most are configured and adjusted on site and can be done with minimal background in control engineering. Just the minimal background you need to know. Okay, to control a system, a simple system. You don't really need to go in deep about. So why we study control engineers? So you'll be able to know how to tune better, and even if anybody can tune, so why yourself so what's this thing? People who are taking control course, you can improve on the controller, understand your system better, and for unstable system is hard to control by doing only tuning. Simple, you keep tuning and you'll never. So I gave the student last year self-balanced robot, ask them to tune it. It's very hard to tune it. So if you go to the lab and try to tune the inverted pendulum, or any unstable system, like in our case the inverted pendulum, it's very hard to tune it if you don't have a model and you don't do some simulation before. So you have a starting point from which you can start tuning. Okay, it's going to be very hard to find the best configuration of 3 parameters. And what if you need 6 parameters? In some control design you need 6 parameters. Or what if you have like a robotic arm with 6 motor or 7 degree of freedom, you have 7 motors, for example, and for each motor you want to add, you have on it PD controller, for example. So then 7 times 2, you have 14 parameters you need to tune, and they are coupled together. Well, to be honest, they are not really coupled. You can control them independently, but they still affect each other. So yeah, some control engineers, like when you control a robotic arm, you could control it motor by motor, but your system is not going to be as good as if you are taking the coupling between each and every link. All right. So having simulation is important in this case, especially for unstable system. So you need to have some control engineering background to move unstable. But if the system is stable, you may know that doing it with minimal background. The minimal background should you have. And by the way, in this course, actually, we're getting the minimal background on control engineering. Okay, so just to let you know. So now you'll be able to tune on site. Before this course, maybe you are unable to tune on site. So this is what you are taking in this course, is the minimal background in control engineering. You cannot say you are really control engineering in this course. Analytical PID controller design requires an accurate mathematical model of the plant. Okay, but if I want to do modeling, this is if I want to compute the PID controller analytically, like doing system identification or so on, this requires an accurate model of the plant. So your physical system, you need to accurately model it. And accurately modeling a system is hard. However, some systems may be too complex to be modeled easily or unknown. Some systems are unknown to be modeled. Okay, then you can do system identification, input output, and I get a response, and doing system identification, identify it to first or second order system or even higher order system. If you are doing system identification in frequency domain, you can get even higher order system, as I was telling you in your project description. Okay, so you can model it by experimentally. so you can still have a model, but that doesn't prevent us of saying that it's complex to model its system sometimes, or it's unknown, so you cannot model it analytically using law of physics. Or the mathematical model in any and every case always is the mathematical model and the actual response of the plan don't coincide. So they are not completely the same. It's not accurate. Okay, here is the explanation of what we mean by not accurate mathematical model. So they are not very same. The mathematical model and the physical system cannot be 100% the same. We do a lot of assumption when we model a system. Even the simple DC motor we are studying, in reality it's not. It's linear system under some conditions, under some assumption. So if you have high voltage applying on it, so it becomes saturated and becomes non-linear, for example. So then, under some assumptions, we model a system. Moreover, the desired location of the closed loop poles required for design of a PID is often trial and error process. Your desired closed loop poles are trial and error process in the sense, like, maybe, as we said, if you have higher order system, the dynamic response of your poles locations, this is everything we studied as was for a second order system, so you can predict the dynamic response if it's second. But if it's a higher system, then you didn't really reach your settling time or your overshoot, so you need to somehow retest the system and tune a little bit to reach your desired behavior. Hence here is the conclusion. So then, if the mathematical model is really sometimes complicated and so on, is there a way to tune it without a mathematical model? There is a need for practical method for deriving okay, in bold, practical method for deriving and tuning PID gains with only the experimental transient response of the system. So now we'll study in the next slide how we can tune the PID with only looking to the experimental transient response of the system. So I have my system at the lab, and then by looking at only the transient response of it, am I able to tune the parameter? Yes, you are able to tune your PID parameter by looking at the transient response of the system. So if you have a system at the lab and you can get out the response on a graph and look at it, as we did in, for example, DC motor control, so we're able to see the response, so then we can do experimental tuning, so to get the parameter. But if you have self-balanced robot and you don't think about to get the measurement, so maybe it becomes difficult in this case. So think about having a Bluetooth that transfer data from your self-balanced robot to your PC and then get output of your response. So this is very helpful to tune your parameter. Okay. Or wire it then, but when you wire it, you will have the effect of wiring, especially if your system is small. So the wire weight will be somehow equivalent to the weight of the robot. So otherwise, if your self-balanced robot is a big, so then you can neglect the effect of wire. So you can wire it wirelessly, get the output to your screen. Anyway, so now how to practically, in this few minutes, tuning the PID parameter. You have two methods, and these two methods are based on extensive extensive experimentation done by Ziegler and Nicholas in 1942, and they established, based on this extensive experiments, they did a lot of experiments, they established a heuristic method that we can use to deduce the PID controller gains. So they did extensive experiments, lot of experiments. If you look to their paper, lot of experiments, and based on it, they concluded about heuristic method we can use. What is heuristic method? This heuristic method is basically, you have two methods you can use. they said to us we have two methods we can use. Propose a set of rules of determining the PI and D parameter based on transient response of the system without knowledge of the system. Without knowing the system. System is a black box. We don't. So there are two main methods. Method 1 and method 2. Okay, so you can use any of them. Sometimes method 1 doesn't work, you go to method 2. Okay, so let's start with method 1. If it doesn't work, so we do method 2. If it doesn't work in the sense like because there is a condition. Here is a condition. So first method is applied only if the plant has no integrator. Like if the plant has integrator on it, for example, so then I don't apply the first method. If the plant has no integrator or dominant complex conjugate poles, actually you can apply. So if has no integrator, if your plant has no integrator or dominant complex pole, so if my plant has no integrator, like if the plant like this, so I cannot apply because it has integrator. If my plant has dominant, maybe it's S3 plus S2, I'm not sure, etc. If my plant or higher order system and the dominant pole are complex conjugate, so then also I cannot apply them. If your system is second order system with complex conjugate, you cannot apply them. So then this method is applied only to if your response is overdamped or no overshoot to step response. Because if complex conjugate means if you are here, so you have underdamped system. So then you cannot apply method 1. So method 1 is applied if your system is overdamped or critically damped, overdamped, or you have no overshoot. This mean critically damped or overdamped. Second method applied if the plants exhibit sustained oscillations with a particular Kp value. So in tomorrow in Wednesday session we'll look at the two methods in detail. So what do we mean by the plant exhibits sustained oscillations with a particular Kp value? Okay, we'll look at it in more detail next time. Just now take it this way, you can explore it yourself, figure out this few slides, coming slides. Note, so then the Ziegler-Nicholas method doesn't apply for every and each system. Really, you should have, according to this experiment they did, they get out conclusion here. That's their conclusion. So it's conditioned of two things. So the plant should have no overshoot, then apply first method, or the plant should exhibit sustained oscillation with a particular Kp value. So does that mean that I cannot apply for every and each? Yes, you cannot apply for every and each system. So, but the majority of system actually they exhibit this behavior. They are critically damped or overshoot, or they have sustained oscillation with a particular Kp value. Most of the system applied for them. Last second, just I want to finish saying this Ziegler-Nicholas tuning is far from perfect. It's based on heuristic method that came based on some extensive experimentation. So it's far from perfect. What does that mean? That means it is employed, this is important to keep in mind always, employed to give an educated guess. As you're modeling, exactly, when you have a model, you have also educated guess or starting point, I was calling it. And from which you can start when you implement in the physical system. So then is employed to give an educated guess for the controller gains Kp, Ki, and Kd, and provide a starting point for fine-tuning rather than final values in a single shot. It's not a final value in a single shot. Okay. Knowing that, next time we will see this important method. Good. If no questions, يعطيكم العافية.
مرحبا دكتور.
يا هلا يا هلا.
يعطيك العافية.
دكتور عندي سؤال.
Yes.